Hi guys, welcome on this video. And today I'd like to discuss about a very important topic in the financial literature, that is the stationarity of a time series. Why is this topic so important? Because in order to make predictions with statistics models such as the autoregressive or the moving average or the ARIMA model, we need a time series be stationary. So if we deep into the finance world, we have to think a time series. So for example, a price time series um, that has a deterministic component and a stochastic component. The stochastic part of the process is the shock, is represented by shocks. So for example, we can think a process in this way. We have a deterministic component we already know, and that is the stochastic part. Stochastic represented by shocks, as I said before. So shocks are temporary and not permanent. So for example, the deterministic part could be a trend or a seasonality, and we can isolate this component. Maybe I can show I can show you this in another video, but the most important thing here is understanding that, for example, this is mu, so this is the average value, the deterministic value. We have price, or to be more correct, this is our process moves above and below the average value, and shocks are not permanent. So shocks are simply deviations from the mean value, from the deterministic value of a time series. So um, what are features for a time series to be stationary? First of all, there are two types of stationarity, in weak form and strong form. To apply our prediction models, to apply our autoregressive or moving average models, we need simply the weak form stationarity. So, sorry. First condition is that the expected value of our process is constant, such as the variance. So the variability does not change over the time. The third condition, more more interesting, is that the covariance of yt and y took taken t minus l lags is unchanged. It does not change over the time, but it only depends by number of lag we choose. So, for example, this is a value today of the process. If lag is equal to 1, this is our value yesterday, the value of the process yesterday. If our time frame is daily, obviously. Well, to demonstrate if a time series is stationary, we can use a very spread test, statistic test, that is the Dickey-Fuller test, also called unit root test. First of all, we have to take in consideration an autoregressive of order 1 process. We can omit the intercept, so we have this type of process. This is the error of the process, and this is the value yesterday. Okay, this is the coefficient, and we are interested to know the value of this one. So our null hypothesis is that the module of the coefficient is equal to 1, while the alternative hypothesis is that this is lower than 1. So the module of the coefficient is lower than 1. Now I am showing you just the simple form of the Dickey-Fuller test. There is also an advanced form, but up to now it is sufficient in my opinion to show you this. So maybe I can show you what p-value means, but for the moment you just have to know that your hope to demonstrate that the time series is stationary is to reject this. You can reject this only having a p-value lower than your alpha. If you want to be strict on your constraint, maybe you can choose 1% alpha, but in general you can choose also 5%. Well, so if your p-value is lower than your alpha, you can reject the null hypothesis and you can affirm that a time series is stationary. Stationarity leads to mean reversion. That is a very important concept of financial time series, and there are a lot of strategies based on mean reversion. Now I will build a Python code on Jupyter to show you how to understand if a time series is stationary. Well, for this example, I'm working with Yahoo Finance. Obviously, you are free to import your own data, but I want to work with Tesla stocks. I will execute the Dickey-Fuller test on Tesla returns and Tesla prices to show you difference about these two types of time series. Price tends to have a trend, so they have deterministic components, while returns are obtained thanks to a transformation, logarithmic transformation in this case, and so financial returns tend to be stationary. So first of all, we need Tesla price from Yahoo Finance. So like I said before, we are using a logarithmic transformation. It is an approximation, but we can work with logarithm, no problems. A very important thing you have to consider is that you have to delete not available elements in the data frame of returns, because the risk is that your code will not work, obviously. So you use the attribute dropna to drop not available values. Okay, now we create a variable called test, for example, and this is equal to Dickey-Fuller returns. Okay, now if you want to visualize every value of the test, the Dickey-Fuller test, you can show the value. This show you the p-value, the different values on the confidence levels, the confidence intervals, etc. But we are just interested to know what the p-value is. If we consider, for example, a 1% confidence level, we can reject the null hypothesis. So the time series is stationary. Um, so we can write this way. So series is stationary. But what happens if instead of returns we choose to use, for example, prices? Series is not stationary. In particular, the p-value will be 22%. So we cannot reject the null hypothesis. This because price have a tendance or a seasonality. So they have a deterministic component inside. And so to have to work with prediction models, we absolutely need to have stationary time series, stationary processes that we can obtain with a differentiation. So that's all. I hope you enjoyed the video. Subscribe and see you in the next video. Bye, guys.